Okay, I think we're about ready to get started. So thank you everyone for coming. Welcome to the September 2020 edition of Space Cafe Tokyo. My name's Ken. I'm one of the co-organizers, along with Mayuko, who's here with me. Mayuko, do you want to show yourself briefly?
Yeah. Hi everyone, thank you for joining us tonight.
And tonight we're very happy to have as our speaker Professor Tamara Davis from the University of Queensland, who will be telling us about the dark side of the universe. So thank you, Tamara. We're looking forward to a great talk. So before we get started, just a short description of us in case this is your first time. Space Cafe Tokyo, we've been doing live monthly events in Tokyo in Shimokitazawa, but unfortunately in recent months due to the pandemic, we've moved to entirely online events. But please follow us on social media at these links here, and we'll post them again at the end of the talk to keep up on future events. And hopefully we'll be moving back to live events at some point soon. Okay, so here's just a picture of the venue we're typically in. It's a bar called Good Heavens in Shimokitazawa. And we've also started a Japanese language version in Roppongi. If you follow our social media, you'll get updates on all of those. And a few notes before we start. So all participants will be muted. If you have any questions for the speaker, you can type them in the chat, either in Zoom or on YouTube Live. And the moderators will pick them up and ask them directly to the speaker at the end during the Q&A session. So yeah, anytime you have a question, just type it in and we'll get to it. Okay, I think that's all of the announcements. Mayuko, do you have anything before we start?
No, it's okay.
Okay, great. So I will stop sharing now, and Tamara, you can start sharing your screen.
Excellent.
Okay, and go ahead, take it away.
Cool. Well, hello everybody. Thanks for coming along. I'm very sorry that we can't all be there in person. I would love to be there having a beer with you or something in the pub at the moment. But the good thing is that I can give this talk to you even though I'm not actually in Tokyo. So yeah, my name's Tamara Davis. I've been an astrophysicist for a couple of decades now. And today I'm going to tell you a bit about the dark side of the universe. So in my blurb that I wrote up, I said that what I would try to do was convince you, if you're not convinced that things like dark energy and dark matter exist, then by the end of this talk, I want you to hopefully be convinced of that, or understand at least why astronomers are so confident in so much stuff that we can't see with our eyes. So let's get started. By the way, if there is questions, please do type them in the chat. I'll pause halfway as well and see if there's any questions yet. I don't mind getting diverted and answering questions that you have rather than talking about the stuff that I'm interested in case those two don't match. So feel free to ask questions as we go. Cool. So I often start my talks with pictures like these. If you have chat there, who knows what this thing is here on the left? I'm going to open my chat. If anyone knows what this is, feel free to type it in the chat. Either that picture on the left or the picture on the right. They're two science experiments, both doing quite different things. I'm not sure if I can. All I can see is at the moment is the Zoom chat. So it might be hard to get quick feedback. However, the one on the left is actually the mirror from the gravitational wave telescope, LIGO. So it detects gravitational waves. And the one on the right is actually a neutrino detector. And this is going to be a massive vat full of water. It's mostly empty at the moment, but you can see these guys on a boat fixing the photodetectors that surround this massive chamber of water that detects neutrinos. Now, one's doing gravitational waves, measuring ripples in space and in space itself. The other's measuring one of the lightest massive particles in nature. And here I am at another big science experiment. This one's the Large Hadron Collider. I can't believe how nerdily excited I got when I got to go into the tunnels here. It was actually really fun. And it's smashing particles together and trying to figure out what the fundamental physics is made of. Now, all of these objects, all these experiments, including this one, the Hubble Space Telescope, are all trying to measure fundamental physics in one way or another. So some of astronomy is looking up and understanding sort of the evolution of galaxies and stuff like that. And some of it is actually trying to figure out the fundamental laws of physics and how they work. And there's a really, really good reason that we look up into space to try and figure that sort of stuff out. And the reason is that it doesn't matter how powerful you make your experiments here on Earth. We can't even in principle go and make something like a black hole on Earth that's like a supermassive black hole, like the ones that is at the center of our galaxy. We really can't accelerate things to the speeds that cosmic rays are, or the energies that cosmic rays are. There's exploding stars. There's billions and billions of years of history to watch. And so you can do experiments, well, you can't do experiments, but you can watch natural experiments happening up in space on timescales and length scales and energy scales that we can't achieve here on Earth. And by doing that, you can sort of look at physics at its most extreme, and you get to see things that you wouldn't have noticed in your little tiny experiments here on Earth. Even our biggest experiments are the little tiny experiments. And it's very, because you can't control the experiments, it's a very different way of doing things. And they're very complementary, but it gives you interesting information. And one of those things two of those things, I guess, are dark matter and dark energy. So my summary of these, if you want to take it to the ultra simple level, is dark matter pulls and dark energy pushes. So dark matter is the stuff that binds the galaxies together. It pulls and holds the galaxies together against themselves spinning apart. It's actually really critical in the formation of all of the structures we see in the universe. Dark energy, on the other hand, seems to be smoothly distributed. Dark matter clumps, dark energy seems to be smooth, and it's accelerating the universe. So it's accelerating the expansion of the universe, making it happen faster, which seems like it's causing gravity to push somehow. Now, what could these things be? So sort of some of the leading candidates for dark matter, as it's a new type of particle that we don't know about. Some people still think it could be tiny little black holes, or some bigger black holes, or some modification of gravity. The leading candidate by far for dark matter is that it's a new type of particle that we just haven't seen yet. We can only see by its gravitational effect. We haven't detected it in any of our sort of normal detectors because it just interacts so weakly with normal particles. What about dark energy? Well, the leading candidate for dark energy is that it's actually the energy of the vacuum itself. So empty space in quantum physics is not actually empty. It has particles being created and annihilated all over the place. And things like the Heisenberg uncertainty principle say that you can never actually have like a zero energy state, essentially. And so the vacuum itself has energy, and it has some really weird properties like negative pressure, which is the kind of thing that could accelerate the universe. So it's naturally there in quantum physics. And so it would be a natural explanation for dark energy. It has many of the correct properties. The problem is the amount of it that is predicted by quantum theory is way off compared to the amount that we actually observe. So quantum physics will predict that you either have a huge amount of it or none at all. And it just varies by, depending on who you talk to, it's up to 120 orders of magnitude wrong. It's a terrible prediction. But we don't have a quantum theory of gravity yet. And so maybe once we do, we'll be able to explain why the energy of the vacuum is so low compared to the traditional quantum physics predictions. Dark energy could also still be modified gravity. It's some sort of modification. Maybe general relativity doesn't work the way we think it does on large scales. Maybe there's a new theory of gravity that will fix it. Maybe it is really, we really do just need a quantum theory of gravity. Or maybe it's something that we haven't thought of. So these are the possibilities. And one of the ways that we go and try and understand them is by observing the universe and trying to observe as many different phenomena as possible and test our theories. So, for example, dark energy predicted that the universe, is a result of the observation that the universe is accelerating. So if we have a theory that says that the universe should be accelerating, then that's well and good. It can explain that observation, but it's not a really sort of, you can't then use the acceleration to confirm that that theory is the theory that is correct. What you really want is a theory to predict something else as well. And then we go and measure that, and it confirms the result that we had from the acceleration of the expansion. And so what I'm going to run through, hopefully, is go through and give you a few of the sort of the leading main pieces of evidence that we have that dark energy and dark matter exist. And I won't have time at all to go through all of the evidence that we have for them, but I'm going to probably give you like the top 5 and about top 5 or 6 and see if that will convince you. Okay, so this picture that you're looking at is a beautiful image of from the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. And it's just a glorious picture of all of these tiny little dots everywhere here are galaxies. There's a couple of stars in this image, like this one with the crosshairs here, and there's one up here. But pretty much every other dot you see is a galaxy, sort of like the Milky Way, with hundreds of billions of stars. And this is a picture that's one of the deepest pictures ever taken. You're looking so far back in time with these that the most distant galaxies that you're looking at emitted the light that we're seeing over 12.5 billion years ago. And the universe is only about 13.8 billion years old. So we're really looking back with pictures like this, basically back to the point where galaxies hadn't even formed yet. It's sort of looking like a tunnel all the way through a very, very narrow little spot of the almost the entire observable universe in that one little narrow direction. And it's that kind of power of modern telescopes which has given us the ability to see these strange phenomena like dark energy and dark matter. Now I'll give it a little zoom out here because it's great fun. This is from a different image, but similarly deep, from the Hubble Space Telescope. And as we zoom out, it's superimposed on images of the same patch of sky, but from telescopes with wider fields of view. And as you zoom out, and you zoom out, and you zoom out, you eventually get to a constellation that you might recognize. And so that's just sort of giving you a bit of hopefully a visceral feel for just how far these telescopes are able to see. It's really phenomenal. And that's a really key part of modern astrophysics, is what we can actually see, how deep we can actually see. Okay, so let's start with the pieces of evidence that we have. Firstly, how do we know that the universe is expanding at all? Well, this was discovered in the 1920s. It was discovered by looking at a kind of star called a Cepheid variable, which oscillates. Its brightness is related to how frequently it pulses. So it gets a bit brighter and fainter and brighter and fainter. And its brightness is, the faster it pulses, the brighter it gets. So you can use that to calibrate the brightness. And it means you can use these stars as a standard candle. A standard candle is something of known brightness, so that if you see how bright it appears, you can tell how far it is away. And that means it's a distance indicator, which is super useful for cosmology, because one of the most difficult things to do in astronomy is to figure out if that bright shiny thing you're looking at is something that's really bright far away or something really faint up close. So if you know its intrinsic brightness, you know its distance, and then you can measure distances to galaxies like this one. The second piece that you need is a velocity. And you get that by measuring the spectrum, the rainbow of light that comes from the stars, and measuring its how the lines shift And when they get shifted to higher wavelengths, that occurs when something's moving away. And so the combination of measuring brightnesses to give us distance and shifts to measure velocities allowed people to see that the universe was expanding. And it was pretty cool because in the 1920s, they'd only just figured out that galaxies were galaxies. This distances basically showed that these spiral things that people were seeing in the sky were not just clouds of gas nearby, they were actually whole galaxies of their own out there. And they weren't even being called galaxies at that point. In the main papers about the expansion, they were called spiral nebulae. And here's a couple of the people that discovered these things. Now, the discovery of dark matter came hot on the heels of the discovery of the expansion of the universe. So I said 1927 was the first paper with the expansion of the universe. It was 1933, just 6 years later, that dark matter was discovered. Here's another character here. The people on the previous slides were, this was Henrietta Swan-Leavitt, who did a lot of the Cepheid variable stuff. And this is Vesto Slipher, who did a lot of the stuff for the spectra. And here we've got Fritz Zwicky, who was the one who wrote the first dark matter paper. Now, he did it by looking at the motion of galaxies in clusters. So galaxies don't form alone. Here, what you're seeing is not what they would have seen back in 1933. This is a numerical simulation done in a computer of the formation of a cluster of galaxies, and these puffs that you see floating around are all galaxies merging into the big cluster in the center. But in that movie, how fast these little puffs of galaxies are orbiting is determined by how much mass is in there, because the more massive the center of the thing that you're orbiting, the faster you can go around without flying away. And so Fritz there, he measured how fast things were orbiting and said, hey, there's a lot of matter out there that we can't see. The amount of mass that's in stars and bright stuff in those galaxies isn't enough to be able to explain the orbits that we're seeing in these clusters. So basically, as soon as we knew galaxies existed, dark matter reared its head and was obvious. It wasn't obvious at the time that it wasn't just dust or something faint that we can't see, but we now know that it can't be dust, and I'll try and get to some evidence for that later. The real strong evidence for dark matter, though, came in the 1960s. And here's Vera Rubin looking at some pictures of galaxies. She was one of the pioneers in this field. And what she and others noticed was that galaxies, like a spiral galaxy like ours, according to how much mass you see, in one of these, the center is very, very dense. And so you need to orbit quite quickly near the center in order to not fall in and get sucked in by the self-gravity of the rest of the stars, etc. in there. But as you go further out, you don't have to spin as fast because you're getting further away from the center of mass. You don't have to fight gravity as hard. And so this was what was expected on the left. But what was seen is on the right. The outskirts of the galaxies are moving almost as fast as the central parts. Now, the only way that we know in standard gravity that could work is if there was a lot more mass here than we can see. So this density that we see at the center has to be a similar density out to the outer parts of the galaxy as well. And again, that can't be in stars, and it can't actually be explained by gas or anything like that, or just dust or something dark. So that's this fast rotation of the outskirts of galaxies was some of the strongest evidence. And this is the stuff that I think really convinced people that dark matter was out there. So as I said, feel free to drop questions in the chat if anyone has any questions. So the discovery of dark energy was arguably even weirder. So ever since the 20s, when they discovered that the universe was expanding, the question on everyone's minds that kept people up at night was, is it the expansion going to keep going forever, or is it going to recollapse? And so here's sort of three possible options of the universe. that the universe starts out from this big bang at the beginning, it expands, and then it collapses and has a big crunch at the end. Or it expands and gravity should be slowing it down because gravity pulls everything together. So one galaxy is pulling on another. If they're moving away from each other, they should be being pulled back together. But is that pull enough to eventually stop them moving away from each other and fall back down, or will they have the escape velocity? Will they be able moving fast enough to be able to expand forever? And so that's the difference between the recollapsing universe and the coasting universe. Cool. So now that was really hard to measure because you can measure the expansion, but it's difficult to measure the rate of change of that expansion, like the acceleration of it. And it wasn't, and the Cepheid variables weren't good enough standard candle anymore. It wasn't until we had something like this, which is how we think a type 1a supernova occurs, that we were able to measure distances to great enough distances that we could measure a change in the expansion. So what you're seeing here is a big star and a little star, close enough together that the little star can suck the material off the big star. Now the little star's a white dwarf, it's dead, it doesn't actually have any nuclear burning going on inside it. And that's because when it died, it was not heavy enough to form anything exciting. It wasn't heavy enough to have a massive supernova explosion or anything. It just sort of died and sat there. But once it gets to sucking this extra material off the other star, it becomes too heavy to support its own weight anymore. And it collapses, and then that ignites a thermonuclear reaction in the center, and it goes boom. And so that's, and interestingly, because there's a really precise tipping point between the mass of a white dwarf that's stable and a mass that's going to explode, that means that these actually have a relatively precise standard candle property. They explode almost to the same brightness, to an extent that we can calibrate how bright they are. But a big difference from the Cepheid variables is that when they explode to basically brighter than an entire galaxy for about a month. And so that one star is as bright as the galaxy. So as long as you can see galaxies, you can see supernovae. So you can see these things really, really far away. So a couple of competing teams got together to do this, competed to do this in the 90s. This is Brian Schmidt, who led the high redshift supernova team, Saul Perlmutter, who led the supernova cosmology project. They're just pretending to fight at a conference here. And this is one of the telescopes that is used to make the observations. Now, what happens when you're trying to find supernovae is you basically go and have a look at a patch of sky, and you go and repeatedly look at the same patch of sky night after night, and you go and see if anything changes. If anything changes, then you think that that could possibly be a supernova, and you go and investigate. So here is my slide that I always show, that shows the before and after. It's the why this is hard slide. And here there is no supernova in the before photo, and there is a supernova in the after photo. If I was there in the room with you, I'd run around the room and I'd pass the laser pointer and I'd get you to guess and have a look at where the supernova is. As it is, I'll give you a second to have a look yourself, and then I'll give you the answer. Okay, I don't know if you've managed to have a look, but to give you the answer, it's right here, that little dot at the bottom of the galaxy. And it wasn't until we had computers that could do the subtraction effectively and check this out that we could tell these little tiny dots, the things that change. The one here is, I think, just an active galaxy that varied with time, and that one's the actual supernova. So, but we're now very good at discovering these supernovae. And here's me hanging out at a telescope because, as I said, just discovering them is not enough. You actually have to get a spectrum and get the velocity of them as well. And this is one of the telescopes that we used to do some measurements of the spectra. It's a really impressive instrument. This is me taking a picture, a selfie in the mirror of the telescope. It's a pretty cool place to go and visit. It's called the VLT. It's over in Chile. And this is where you live under this dome when you go and visit the VLT. It's so cool a place that they used it in the James Bond film. And here they're blowing up the using CGI, luckily, the astronomer's residence at the VLT as part of Quantum of Solace. I stayed in this room down the bottom, the third one just from the edge. But to put it, long story short, once you measured the standard candles and the velocities, you could measure how fast the universe was expanding in the past, because the things that are very far away, you're looking at them as they were in the past. And so you're measuring the velocity of galaxies in the past. And you're looking at supernovae closer, and you're measuring the velocity of the galaxies that hosted the supernova much closer. And you can tell then whether the expansion has sped up or slowed down over time. And that was the surprising thing, that in the recent universe, the universe has actually been accelerating. It decelerated a bit for the beginning, and then it started to accelerate. Now, it's immediately solved a whole bunch of problems. One of the most important ones is it solved the problem with the age of the universe. So you can see here vaguely that the slope of these lines are all about the same at the present day, which is this red line through the middle. If the universe decelerated to that speed of expansion, that slope, then it's not very old. But if it first decelerated, but then accelerated to get to the rate of expansion that we observe today, then it's much older. This point here is much further back in time, which is convenient because people who studied stars could see that the oldest stars in the universe, close to 14 billion years old, and they couldn't fit in a universe that was only nine and a bit billion years old, which is what the decelerating version of the universe was. And so the fact that stars exist that are close to 14 billion years old is one of the biggest pieces of evidence that there's dark energy. It explains the age of the universe problem. And that's quite apart from actually measuring the acceleration itself. Oh, there we go. And so for that, these guys got the Nobel Prize. But there's more. There's a lot more evidence that goes this, but this might also be a good point to pause and answer a couple of questions if you have any. I see a couple on the chat here, but I haven't had a chance to look at them. Are there any, have the moderators found any good ones that I should particularly look at?
We can take maybe a question now or save them all for the end. What do you want?
Let's do a question now.
Okay, so let's take a question. First question from Yuri. Wouldn't the center of the universe still be denser than the outside? Is there a reason there's less dark energy in the middle? I'm guessing Yuri means center of the galaxy? Or maybe
yeah.
maybe center of the universe, dark energy. Okay.
Yeah, I'm not sure. So there's two questions, because if you mean the rotating galaxies, the center of the rotating galaxies is still denser than the outskirts, but it's not. But you just get more matter in the dark matter cloud than you would otherwise have had if there wasn't any dark matter there. But for the universe, what we understand is there actually isn't a center of the universe. So everything is moving away from everything else. And so the way that the density works for the universe is, my best analogy is, imagine you have a balloon with a whole bunch of dots on it, sort of, they can be evenly spaced, they can be randomly spaced, whatever. And I blow up the balloon, every dot moves away from every other dot. So if I picked a dot and then I would see how fast things were moving away from it, the nearby dots would be moving just slowly because there's not much sort of rubber of the balloon nearby. And then the more distant dots would be moving away more quickly because there's more rubber to stretch between. And you get a rule so that the velocity is proportional to the distance, which is what we observe in our universe. But I could pick any dot on the balloon and that would be true. And so my reassuring point to you today is that there is no center to the universe, but in a way, everything is the center of the universe. So I can confirm that you actually are the center of the universe. I'm not
Great.
sure if that fully answered the question.
Do you want to take another one or do you want to continue?
Sure. Let's do one more and then I'll continue.
Okay. Mayuko, is there one from YouTube?
No, so you can go ahead.
Okay, next question from Irsad Majid. Could we locate the position of dark matter? Also, we have efficient methods to identify dark matter and detect it.
Sure. So we can locate the position of dark matter by its gravitational effect. So we can see how it, as I said, we can tell that dark matter clumps. We can tell that it clumps around galaxies, and clusters of galaxies are full of dark matter. I can't tell you whether there's some in my hand right now. There probably is, but we don't really have efficient methods to detect it if it's a particle, because one of the key characteristics of dark matter is that it just doesn't interact with electromagnetism. So electromagnetism is the main force that photons are related with. And so the photons of light, that's why we call this dark matter, because it doesn't interact electromagnetically. And so it doesn't bounce, it doesn't hit particles and so we can't detect it with most of our usual techniques. And so there are tricky ways that people are making dark matter detectors and things that are very clever, but they're sort of a bit shots in the dark sometimes, because they're saying, well, if it interacts a tiny bit in this way, then this will detect it. But if it interacts a tiny bit in this way, then this other thing will detect it. And so people are trying all sorts of different ways, but we don't have an efficient way for sure to detect it yet. Okay, so I'll dive on now and keep the questions coming. I love it. So let me give you a flyby of a couple more pieces of evidence for dark energy and dark matter. First one is the light left over from the Big Bang, the cosmic microwave background. Okay, so this is a picture from the Hubble. This is the Hubble Ultra Deep Field that I showed you before, and I said that here we're looking almost back to the beginning of time, to the time when galaxies no longer existed. But if we look past this and go even further, we are left with some microwave radiation, so some light that has microwave wavelengths, so quite long wavelengths. You detect it sort of like with radio telescopes, the big white dishes type of thing. And this is an all-sky image taken by something called the Planck telescope of the pattern in the light left over from the Big Bang. Now, this is what you're looking at here is back at the point where the entire universe was basically as hot as the surface of our sun, pretty close. And you're seeing hot and cold spots that correspond to sound waves and compressions and rarefactions of sound waves, as well as some gravitational effects that were going on in the early universe. But I'll get to that. But if you lived back at the time this was emitted, which is about 380,000 years after the Big Bang, it would be like living within a star. In the outskirts of a star, just a star that extends every direction that you go. It would have been really, really hot, and it would have been really, really dense. Now, these guys won the Nobel Prize for this paper that was called A Measurement of Excess Antenna Temperature at 4080 megacycles per second, which is megahertz. And what they discovered was there was just this radiation everywhere they looked. They thought they couldn't understand why it was there or where it was coming from, and why they couldn't get rid of this noise that they thought was in their telescope. And it turned out that this noise was actually the radiation left over from the Big Bang. If you are old enough to remember an old analog television, then a bunch of the static that you used to see on an analog television was a couple of percent of that was actually radiation from the Big Bang interfering with your antennae. Now, a second Nobel Prize went for this picture, which was taken by the Kobe Space Telescope. It's a whole sky image, and you've got the hot and cold spots here in relatively low resolution compared to our modern ones, but just measuring these at all was a massive breakthrough. The difference between these is only a 10 to the minus 5 Kelvin. So it's the whole temperature of this is about 2.7 Kelvin, and the hot and cold spots are 10 to the minus 5 different from each other. So it's almost perfectly smooth in all directions of the sky. And these tiny little fluctuations are key to some of the structure that we can see in the early universe. So This is the modern version of that. This is taken by the Planck Space Telescope, and you can see a lot more detail in here. Now, the patterns in here were predicted. You can predict what's going on by starting from completely random initial conditions and then going on and seeing how that really hot, dense gas of the early universe, using very simple physics, actually, just how sound waves propagate in the presence of gravitational fields and other things in a plasma. And you predict the patterns you would see. You can't predict that this spot will be hot and this spot will be cold, but you can predict that if this spot is hot, the likelihood that a bit beside it, this spot is also going to be hot. And that's because this would be the peak of a sound wave, and so would that. That kind of thing is what you're actually observing. And this is a plot of the patterns that you see. So here you've got the strength of the fluctuations as a function of separation. And the red line is what you would sort of predict if you had the amount of dark matter that we see in rotating galaxies and in clusters of galaxies, and the amount of dark energy that we detect in the that would cause the acceleration of the expansion of the universe that we see. And the blue dots are the data points, and it's just a gorgeous fit. Like, I mean, that's an amazing fit of a quite complex model to the data that's observed. So this is a more precise measure of both dark matter and dark energy than the original measurements. And so this model has smaller error bars than you had from the other ones. And so it makes this one of the real powerhouses of the measurements of dark energy and dark matter. And to show you just how sensitive this is to those dark elements, if I took the dark energy out of this model and did nothing else, then that's what the power spectrum, what the prediction would look like. Whereas if I took the dark matter out of this model, then that's the prediction that it would look like. And so you can see that dark matter and dark energy have a really strong impact on the pattern that we see here. And it's really hard to explain this cosmic microwave background without them. And it's such a weird thing, basically. Like the physics behind this is plasmas and sound waves and stuff. It's very different to the physics of rotating that you have in a rotating galaxy or the acceleration of the universe. And so the fact that this agrees with the dark energy and dark matter predictions from the other ways of measuring it is a really strong advocate for the fact that this is really out there somehow. Okay, I better go a bit quicker because I've still got two more bits of evidence that I want to get through. And that was just to explain, I've mentioned a couple of times that these sound waves are out there in space. Now, this is actually one of the most profound things that I think I've learned about the universe. If you start from completely random initial conditions, you can get patterns, you can get structure, like that plot that I was just showing. So here's just showing if you have a bunch of different random fluctuations in the universe, the dark matter doesn't propagate with sound waves because it doesn't interact very well, so it just stays in these little peaks, and these circles form where that's actually the normal matter propagating as a sound wave out of some random initial fluctuation that you get. And this would form the pattern that you see in the cosmic microwave background, a whole bunch of overlapping sound waves, like as if you threw a whole bunch of rocks in a pond and you're looking at all of the waves overlapping with each other. But what they are dense parts and underdense parts. And what happens when you have a dense part and gravity? That dense part is going to collapse under its own gravity, and that is actually where galaxies form. So it turns out that the pattern of galaxies that we see in the sky is not actually random. It's related to the patterns that we were seeing in the cosmic microwave background. And you can go out and measure that pattern. And because there's a sort of sound wave pattern in there, hidden deep in overlapping waves all over the place, if you measure enough galaxies and measure enough separations, you can measure that sort of characteristic scale, which is what you're seeing here in this bump that you would see. There's a baryon acoustic oscillation peak. That BAO peak is a scale that we can measure in the distribution of galaxies. It comes from the sound waves from the early universe, and it acts as like a ruler. And we can use that to measure because we can measure how big the ruler appears at just different distances, we can again measure how far that is away and measure how much the universe is expanding. So it's basically like laying grid paper over the universe and being able to measure its expansion at different times. And doing this has also confirmed that dark energy is out there, that the universe is accelerating. Now we do that by chucking things into numerical simulations like the one I was showing you before, where we start from very smooth random beginnings and we see galaxy clusters forming and things. And the way that we actually measure it is by going to telescopes like the Anglo-Australian telescope here. And this is the 2-degree field instrument. And it's pretty cool. You put optical fibers, this robot puts optical fibers at the positions of interesting galaxies that you want to map. And you get spectra down each of these and use this to measure the velocity away. And this is sort of helps us measure the distances and stuff. I'm going a bit quickly to wrap up, but these are the kinds of maps that you can make with that kind of instrument. This is from the 60F, but here you've got to imagine that we're at the center and every little dot that you're looking at is a galaxy that we can see. Now we can't see some things, like this slice down the bottom is where our own galaxy gets in the way and we can't see. And this particular survey didn't look in the Northern Hemisphere, so we don't have any data up there. But otherwise you can see this sort of map of the sort of filamentary structure of the galaxies as I flick through a couple of different surveys that have been done. You can see sort of those patterns until I'm going out further and further to greater and greater distances as we go here. And this is one called the Wiggles survey, which I was part of. And you use the distribution of galaxies there to measure those patterns and measure the expansion. And that too confirmed the amount of dark energy and dark matter that the other probes had tested. Okay, and one final exciting thing. In my incomplete list of exciting things that show that dark matter and dark energy are out there, and that's gravitational lensing. So when we look at distant light from a distant galaxy, if it's behind a galaxy cluster, then that light can reach us by multiple paths because the light gets bent as it travels through curved space. So we might see the same galaxy in different regions of the sky. And so let me give you a picture of this. So here what you're looking at is a cluster of galaxies in the foreground, and this blue galaxy in the background, you can see multiple times. This galaxy here is the same as the one over here, and the one down here, and this one up here, and this here. They're all the same versions of a distant galaxy seen by light that has followed different paths through space to reach our telescope. Now, this is really cool because the amount that light bends is determined by how much matter is inside there, by how much mass there is. And you can do the calculation for how much bending you would expect given the stars and gas that you see. And again, it's not nearly enough to explain how far away these patterns are, because the further away they are, the more light has had to follow, the stronger the curve in the path that light has followed. And there's many, many, many pictures of like these. You can see all of these arcs around the side. There's a couple of background galaxies here, but you can see all these arcs are all evidence. They sort of line up in circles around massive clumps in the center. And people can make maps of the distribution of mass in the center. And here you see these spikes are galaxies, and the sort of overall big smooth shape is the lump of dark matter that we think is basic. Well, there's dark matter in the galaxies too, but you can see you can actually make very detailed maps of the mass that you see in these galaxies, and that is also evidence for dark matter and dark energy. Okay, so there's some more pretty pictures here, and I won't give you much of a talk about weak lensing, but this also happens where basically even if you don't see multiple images of a galaxy, all of the light that comes to us is bent and warped in some way. This is far over dramatized, but anyway, you can use that to make maps like this, which is one of the biggest maps of dark matter that we have. It's several billion light years across. It was made by the Dark Energy Survey. And these, again, you see dense spots and underdense spots, and those correspond to sort of the matter distribution that we see in the universe. Okay, so rather than going on to any details of the Dark Energy Survey, I'll just wrap up that there's a lot of dark matter out there and a lot of dark energy. And here's some of the properties. Now, I haven't gone through all of the evidence for them. I just gave you some sort of like the really big ones. But hopefully you're convinced that it's not just spinning of galaxies, it's not just measuring supernovae and the acceleration of the universe. There's things like just the age of the oldest stars, there's the cosmic microwave background, we've got gravitational lensing, we've got the distribution of galaxies, and we've got both strong and weak lensing. And all of these things combine to give us a picture that dark energy and dark matter are out there and are really something that we really do need to explain. And hopefully the next generation of astrophysicists will actually be able to explain that. Okay, thanks.
Okay, thank you, Tamara, for a very nice talk. Okay, so we will have a question and answer session now. So if you have a question, please type it into the chat. Mayuko, are there any from YouTube?
Not now.
Okay, so I will ask a question from Mayuko, actually.
Yeah.
If, well, you can ask it then.
Yeah, I just wondered if if the dark matter doesn't exist, it means in the center of the galaxy, the rotating speed is faster, then I guess the structure of spiral arms will change. So what do you think? Is it? My guess is that it's going to get thinner when it goes inward.
You mean thinner?
No, it's like
thinner stripes going around?
Yes.
I'm not sure in detail, actually. I don't know a precise answer to that. Would have to think about it, or would have to do some modeling. I don't know if anyone's looked in detail at that. But the dark matter is quite smooth, and in any particular point, it's not particularly dense. It's just dense once you take the cumulative sum of it through the whole sort of cloud that goes around the galaxy. And we think the dark matter is probably much more spherical than the galaxies because it doesn't have the friction that would cause it to lose some of that energy and form into a disk. So the dark matter will be much smoother and it won't necessarily disturb the pattern of spiral arms that much. Is my first instinct, but haven't looked at that one in great detail.
Yeah. Okay. Thank you.
Okay, are there any other questions either through Zoom or YouTube? So I'll chime in and say, yeah, one question that I get asked frequently by like sort of my non-science friends is like, what's going to happen? What's the ultimate fate of the universe? And I give them sort of the standard answer of, the heat death scenario, but there are a few other more exotic possibilities. Did you want to mention a couple of those?
Yeah, so if I did talk about the fate of the universe here as to whether it was going to recollapse or expand forever, or as the case may be, accelerate as the universe goes. Now, so this one would be the big crunch if it collapsed. We think that's unlikely because it looks like the universe is accelerating, and once it started to accelerate, if our understanding is correct, there's really nothing that would stop it and turn it around again. That said, we still don't know what dark energy is, so it could be something more exotic. If it accelerates like this, it will just it will end up. If it's just vacuum energy, it will end up accelerating at an exponential rate, which is sort of just like going towards a sort of a steady state of accelerating more and more and more and more and more. And that's okay. There'll be it'll just get cold. Black holes will die. Things will fall into black holes. Black holes will die. It'll just get very cold, empty universe. But there's even a more exciting one, because if you have the universe accelerating, you have an event horizon. There's a distance beyond which light can't reach us. And if it goes exponentially, then the event horizon will be a fixed size. So there'll be a fixed size beyond which the light can't get to us. But if you happen to go faster than exponential, you can get a scenario that's even more dramatic, which is the big rip. And the event horizon gets closer and closer to you. And when that happens, things can't even hold themselves together. So if whatever exists left, even atoms and things, would get ripped apart as the event horizon came closer and closer to us. Now there's good reason to think that theoretically that's an unlikely scenario, but we can't rule that out as a possible fate of the universe. There's no real fate of the universe that makes life happy.
Okay, so we have one more question from Yuri. What kind of study are you doing right now?
Oh, well, isn't that convenient? Here's one I prepared earlier. One of the projects that I'm working on at the moment is called the Dark Energy Survey. And so we're making a massive map of the distribution of galaxies, and also measuring supernovae to try and really pin down the acceleration and test whether that acceleration of the universe changes with time or not. Because there are some theories in which if the acceleration changes with time, you would be able to, well, some theories predict a changing acceleration and some don't. And so the Dark Energy Survey is really cool. This is one of the images from the camera that we have on the Blanco 4-meter telescope in Chile. And just in one image, you get an image that's about 8 times the size of the full moon. So it's it's really large, and you get spectacular detail across the whole image. And so one of the things that basically we did ended up being a 6-year survey. This is a picture sort of the whole sky, and this is just sort of the affectionately known as the tank section that's filled in by this is sort of the patch of the sky that we're looking at. This is along the equator, which is why we have the big stripe, and then this sort of big patch which is between the galaxy. And we then get spectra of that as well, and we can measure supernovae going off in the galaxies in there. So this is an example of a pretty supernova that we found really close. And with that, we can, the picture that was the weak lensing map that I showed you, mapping the distribution of dark matter, is one of the things we did there. And this is actually a little animation that some of my students made, showing supernovae going off in these really thin pencil beams of the survey that we're looking at for time-lapse sort of spectroscopy and photometry to look at how things change. So this is one of the big observational projects that I'm working on at the moment, to try and understand and measure more precisely what the dark energy and dark matter might be. Oh yeah, I forgot to mention, when we made this map, this was only 27 million galaxies that helped make this map, but we've now got over 300 million for the final map that's going to be made, which is really exciting.
Okay, Mayuko, are there any questions from YouTube?
Now you can go ahead with another question from Zoom.
Okay, so there's one more question from Zoom. Let's make this the final question then, from Antara Day. How will different dark energy models affect star formation?
Oh, good one. So early on, dark matter or dark energy is not very significant. It becomes more and more significant as time goes on, because early on in the universe was still quite dense, and the attractive force of all the matter was the dominant feature. And so early star formation and stuff is basically, and the formation of galaxies was not super affected by dark energy. It's only that once the galaxies had formed, sort of about 7 billion years ago, that the universe started accelerating. And so the galaxies sort of stay together, and they hold on to most of their gas and stars and things like that, and would reprocess and do star formation in there. And they sort of don't care a hell of a lot about what dark energy does. But what dark energy, the main effect that dark energy will have is that it will prevent more gas from falling in. It will prevent galaxies from merging. It sort of pushes the galaxies further apart, so they will run out of gas to make stars. For an individual star, dark energy is almost entirely unimportant, we think, because it, like in our solar system, like I'm attracted to the Earth, right? And our sun, or our Earth is attracted to our sun. And in the scale of a solar system, the dark energy is so tiny in effect, it's not even noticeable. It only becomes noticeable once you go out to big supergalactic scales, because that's the point at which there's enough empty space, which is empty space being filled with dark energy, which is when the dark energy starts to dominate. There is some interesting options for dark matter inside stars, because dark matter could clump inside stars and change the thermonuclear processes, the rate of reactions and things like that. And so some people are actually looking at stars as a way of testing the dark matter theories, because some dark matter theories would predict things that are too extreme a change in stars compared to what we observe. And so you can rule out dark matter theories that way.
Okay, so I think that about wraps up for the question and answer. So thanks again, Tamara, for a very nice talk. It was very informative. So yeah, great. Okay, so you stopped sharing. So I'll just end with a few announcements. Let me share my screen. Okay, so this is just our advertisement poster again, but you can follow Tamara on Twitter. Her Twitter handle is listed right here at Tamara Astro. And so normally at our live event, we charge an entry fee, but that gets you a drink ticket, which supports the venue and all that. Obviously, since we've moved online, it's free to participate. But if you're so inclined, we would appreciate if you consider donating to the International Astronomical Union. They do a lot of work for both education and outreach. And so if you want to support astronomy and its contribution to societal change, please go to iau.org/donate. So our friends over at Nerd Night Tokyo have also been doing online events for the past several months. Their next event is going to be on October 16th. You can check them out on Facebook and Twitter at these locations here on the screen. If you have a question about space or astronomy in general, you can go to this web form here. You can check out the QR code or go directly to the address. We are planning at some point in the future to have either a panel of astronomers or maybe just a general, ask an astronomer type of event where we will answer several questions that we take through this web form. So please check it out. And we've also advertised this on our Twitter and our Facebook, so you can get the link from there as well. So please follow us on social media so you get informed about all of our future events. And I'll just acknowledge the Space Cafe Tokyo team. So I'm Ken, and Mayuko was here helping me today. And the other main organizer is Tilina, who unfortunately could not be here today. We also have a Japanese language version of Space Cafe Tokyo, which is run by Ayako. And when we've been doing our live events, we have Michelle, our photographer. Hopefully we'll be back at the live venue and get her to take some pictures again soon. But this is the Space Cafe Tokyo team. And our next event, the date has not yet been decided. It will be sometime in October, and it will be online again. We're not quite sure when we'll move back to live events, but the October event will be online. So please follow us on social media again to get informed about when that will occur. Okay, so with that, I think that is the end of the event. And thank you again, Tamara, for the talk, and hope everybody has a good evening.
Thanks for having me. Bye, everyone.